Okay,
Okay, I'll
so
do the short route.
this question, let's walk through it. So you have um, basically there's energy being used to warm a cup of water. That's what this like first paragraph is telling you. And then we want to know, the question is how many photons are responsible for doing that. So with any question, let's just highlight what they give us and see what we want to find. Okay. So photons are responsible for the warmth we feel. Okay. These photons warm other objects. So we have photons with this specific wavelength, and in order for the water to be warmed up, they have to absorb those wavelength of photons. So we're warming up water um, with that much mass from 25 to 40 degrees Celsius. So that's what they give us. Okay, so moving on. The amount of energy required. So Q here is heat or energy, because heat is a type of energy, yeah? The water will be determined and found by, so they give us this equation to use, which is nice. And then we have C, that is the specific heat capacity. I'll get into that later. And change in temperature. And then they want us to figure out how many photons are there. So let's write everything down. So we know that the wavelength is that. So this is the lambda. It's like a Greek letter they used to represent wavelength. So 1.5 times 10 to the negative 6 meters. Okay, and we're using water. The mass they gave us was 175 grams. And our temperature change, which is delta T, that just, you take the final temperature and you subtract it from the initial one. So our final temperature was 40 degrees Celsius and our initial one was 25 degrees Celsius. So that means the total temperature change was 15 degrees. And that makes sense. It was a positive change in energy. If it was cooling down, then this number would be negative, because it would affect the math and everything. So that's good to double check the sign. And C, that is the specific heat capacity. And here, let's write it down first. Joules per grams degrees Celsius. So every material, like the question said, like we feel warmth, and you can also warm objects. Okay, now this C, the specific heat capacity, tells you how much energy is needed to heat 1 gram. So how much energy, joules, to heat 1 gram 1 degree Celsius. So for water, in order to heat a gram of water by 1 degrees of Celsius, you have to use 4.2 joules of energy. And this is different for every material. Water has a pretty high one. You'll get, like, you can Google these values. There's like data tables they give you, like aluminum has one, sand has one, you know. Every material is different, so that's why we have to use the one for our specific material, which is water. That's why I highlighted it in the question. Because if we were heating up like aluminum, then we would have to use a different value. Okay, so, and then they also gave us, how nice of them, they gave us a little equation to use, which I'll, yeah, right, Q equals MC delta T. So, yeah, we have M, we have C, and we have delta T, so that's nice that we can solve for heat. Okay, so instead of just blindly doing math, let's kind of think about what we're trying to achieve here at the end. So again, we're trying to find how many photons are in this system. Now, in order for us to find how many photons there are, this equation right here is helping us solve for heat. Yeah? And like I said before, heat is a form of energy. So once we solve for heat, then that is like the same as energy. And photons and energy are related, right? Because every photon has a wavelength, has a frequency, and that'll help us piece everything together. Remember how like moles and molar mass was used to convert from mass to whatever? In our case, heat and wavelength and photons, those are all the related bits that you can kind of convert from one form to the other. So once we know Q, once we know how much energy was needed to heat 175 grams of water, then we can use that amount of energy to help us determine how many photons made up that energy. Okay? So now we can just plug away. So Q, how much mass? There's 175 grams. And actually, before I go on, I think it's just a good practice to make sure our units are all or that they work together. So we have grams here, Celsius, and then joules, grams, degrees Celsius. So right now this looks good. There would be red flags like if this was like 0.175 kilograms, we would notice, hey, you can't cancel out grams and kilograms. You have to convert from one form to the other, right? So, or if the Celsius was in Kelvin, you'd have to convert that first. But you see what I mean? Just to make sure that our math lines up, just make sure that your units are related. Another side note I will say is that they were nice and they gave us our temperature in Celsius because, which is nice because like all our values, or the specific heat capacity, it gives us that in terms of Celsius. But Kelvin, that is another form of temperature unit. So pretend it was like 275 degrees Kelvin and it heated up to 300 Kelvin. You want to find the difference first before you turn it into Celsius. Yeah, so hold on, let me think. So the difference would be... Actually, no. I think you should convert this to Celsius and then find the difference. Because the difference between these numbers does not equal the difference in... Okay, you know what? I think I'm confusing you. Because I'm confusing myself because I mess up that stuff too sometimes. So, sorry. If in Kelvin... convert to Celsius first, then take difference. I will double check that for you, but let's just, because some questions do give you that in Kelvin, so anyway, moving on with our question. And then we have our specific heat capacity. Remember, this is how much energy is needed to heat up 1 gram of water. Too bad we're not using 1 gram, so we have to do this. Okay, and our energy change was positive 15 degrees Celsius. Perfect. Now, like I said, it's important to look at units. Helps you make sure you're doing the right math. So let's cancel out grams and grams, because this is on the denominator. Celsius on the bottom, Celsius on the top. Which is good. We're left in joules, which makes sense because the question said Q is heat. Heat is energy, and joules is a unit of energy, which is nice to see. So yeah, let's put this in our calculator. 15. Okay, so I got this number. So again, this is the heat or amount of energy needed to heat up 175 grams of water from, what was it, 25? Yeah. 25 to 40 degrees Celsius. Okay, and we're not done because first of all our question's asking us number of photons. Okay, so now we need to kind of think a little deeper. So yeah, we can call this like system energy. So this is the amount of energy our system needed to heat up. Now we have to relate the energy to the number of photons somehow. So how do we do that? Okay, so another very useful equation, it's pretty simple, is this, which is basically the energy of one photon. And every photon will have different energy because, like UV light, X-ray light, visible light, they all have different frequencies and wavelengths. And of course the visible light spectrum is just the colors we see, but we can't see UV light, right? Because they all have different wavelengths and different energies, right? So yeah, that equation is nice because we wanted to relate energy to photons, and look, this equation is literally telling us the energy of a photon. So that's what the E term is, the H. This is called Planck's constant. Yeah, just like Avogadro's number, it's just a number. I don't really know how it came from, how he discovered it. I just use it, so. Yeah, that's joules times seconds. And then V, this is frequency. Okay, so we want to find E, and that's a constant. Yes, we want to find E. We have a constant, but frequency, we don't have frequency. So how do we, because we have two unknowns, like how do we solve this? Well, we're in luck because the question gave us wavelength. And that is related to frequency because, like I said, each photon has a specific wavelength, and wavelength basically tells you information about frequency. So, yeah, we can convert from frequency to wavelength super easily with the next equation I'm going to show you. So, we had, what was our frequency? What was our wavelength? 1.5 times 10 to the negative 6. Okay. Meters. Okay. So we need to use a different equation in order to convert from wavelength to frequency so that we can use this equation. And what that is this right here, where c is the speed of light. And again, this is just a constant. You can Google it. Times 10 to the 8 meters per second. Lambda, we said that was wavelength, which is good because we know the speed of light and we know wavelength. And we solve for frequency. Once we solve frequency, we can use this. And once we have E, we can relate it to our system and we'll be good to go, hopefully. Okay. So yeah, we just, if they gave us the frequency, we could have saved a step, but because they gave us wavelength, we have to just convert it to a frequency. So if we want to isolate for frequency, we'll just divide both sides by lambda. So yeah, now I just plug in the numbers. And again, check 4 units. Hooray, we have meters that cancel out. Very good. If one of them was nanometers, we just have to, usually wavelengths can come in nanometers. So yeah, you just have to use Google or just like convert it. So there we go. Which is good because, sorry, I didn't tell you, frequency is in the units 1/second. So, which is good because we have seconds up there, which is on the denominator. So good. Yeah, and just put that into our calculator. And then frequency, yeah. Okay, good. So now that we have frequency, we can use our energy of one photon equation and figure out. Because, yeah. Sorry, just backtracking. So this Q gave us the energy of the system, and E gives us the energy of one photon of that system, which is useful because we need to figure out the number of photons, right? So, and yeah, Planck's constant was look for units, seconds cancel out, and we'll be left with joules, which is a good sign because energy, joules is a unit of energy. So put that into our calculator. Every time I type this number in, I get a brain fart. I don't know why. Okay, so accordingly, one photon has this much energy. Okay. Are we done now? No, because this tells us, again, just the energy of one photon. And we know the energy of our system, which has photons in it, of course, and then we know the energy of one of those photons. So now we can move on to our last step. So, what was it? 10983. Yeah, was that correct? Cool. So, this was energy of all photons, right? Because it's the system. And this is energy of one of those photons. Okay, so now it's just a matter of dividing. So, yeah. So we should take the energy, sorry, yeah, I think, yeah, so total energy divided by the energy of one photon should give us the total number of photons. So, let's see if that's right. Again, the units line up. Divided by the energy of one photon. I guess joules, yeah, per one photon. I can just say per photon. joules will cancel out, and then we should be left with photons. So hopefully we get a number that makes sense. Okay, and I think that looks good to me. Times 10 to the 25 photons. And it looks good because we have times 10 to the 22, and your question gave us that. So that's a good sign. Okay, I feel like you might need to round for this question, so let's just go over that. Our significant digits. Basically, we use the least number of significant digits. So 1.5, that has 2. 175 has 3 significant digits. This has 3. This has 2. This has 1, 2, 3, 4. So the least number is 2, so we should round our answer to 2 significant digits, which equals 8 point, that'll become a 3 times 10 to the 22 photons. And the times 10, that never counts for significant digits, it's just the first number. So hopefully that is correct. And yeah, let's just walk through what we did again. So it was nice that the question led us on. It was like, you're heating up water. How many photons are in that amount of energy, basically? So yeah, so remember this equation. Remember Q is heat is energy, which probably in joules, or it could be kilojoules, whatever, different metric system. And then this is energy of a photon, and this is just used to convert from each other. If you just wanted to like save yourself a step, E equals HV, and we know that V equals C over lambda, you could just do this, right? Because the math doesn't lie. This is equivalent, so we can substitute it in. So yeah, that you could also do that. It would work out just fine. Yeah, and then once you have the energy of one photon, and you know you have your total energy, you can find your way. Okay, hopefully that helps. Sorry.